And now we're going to look at a theorem that's really important for the remainder of the course. It's called the invertible matrix theorem. And it gives us equivalent conditions that help us to determine information about matrices or transformations just based on other information that we know. So let's say that A is a square n by n matrix. The following statements are all equivalent. So that means that if you know one of these is true, all of them will be true. Now, we've gone through this information in smaller pieces previously. For instance, A being invertible. If A is an invertible matrix, then we now know from what we just did in the last section that A is row equivalent to the identity matrix of the same size. Okay. We also saw in the previous chapter that A would have n pivot positions. Okay. That was equivalent to the equation AX equals 0 having only the trivial solution. Okay, or the columns of A forming a linearly independent set. Okay, so we've tied these together in different ways. The fact that it's row equivalent to the identity matrix makes it have the n pivot positions as well. Okay, the linear transformation, we discussed linear transformations T previously and tied them to a standard matrix. So when we had a linear transformation T going from Rn to Rn, or this would be Rn to Rn since we're talking about an m by n matrix, there's a linear transformation T that then is tied to that standard matrix so that T takes in vector x to whatever the product is with that matrix A. Okay, so when we had that linear transformation, it was 1-to-1 when the matrix A was invertible. Okay, the equation AX equal B has at least one solution for every B. Now that's equivalent to being 1-to-1, because being on-to. On-to was when you took a vector here, so any B that's in Rn, is there some x over in Rn so that Ax is equal to that B? And that's what this statement G says. The equation Ax equal B has at least one solution for each B in Rn. The columns of A spanning Rn, that's telling us for every vector over in Rn in that codomain that the columns spanning it means, remember that Ax was where we took linear combinations of columns. We took the columns of A, which were A1, A2 to AN, and then times some x vector. That product was just a linear combination of the columns of A. Okay. So that meant that if you took a B in the codomain, if the columns spanned, that meant that that B was a linear combination of those columns. So that's the idea of spanning the space. The linear transformation from X to AX, that's our transformation T that we're referring to, it maps Rn onto Rn. Now that's true because we know that every vector in the codomain has some x that maps to it. That makes it onto. Okay. There, just most recently when we've talked about inverses, if we have an invertible matrix, that means there's some n by n matrix C so that C times A is the identity. Likewise, there's some matrix D so that A times D is the identity. Okay, and the transpose of a matrix that's invertible is always invertible as well. Okay, so if we have that C times A is equal to A, and we know A is invertible, that means that C is the inverse of A. Or that would mean then that A was the inverse of C. And likewise here, A would be D inverse, and D would be A inverse. Okay, so those are equivalent conditions that if you know one of them's true, then you can get the other information from that. So sometimes, depending on the situation, some of it's easier to find or show than others, and then we'll be able to get all the other results that are equivalent. So refer back to this, keep it handy so that you can refer back to it when you need to. Okay, so I want to use the invertible matrix theorem to decide if this matrix A is invertible or not. Okay, so some of the things to show it's invertible. If the columns were linearly independent, we would know it was invertible. So we could check that. We could check to see if the matrix could be row reduced to the identity. That's probably the easiest thing that we can do. So let's just do that. Let's do a row reduction. Leaving row 1 alone. I'm going to take -3 times row 1 and add it to row 2. That'll make this 0. This is -3 row 1 added to row 2. And that's this new row 2. Okay, so that's going to give me 0, that's going to give me 1, and that's going to give me 6 minus 2 is 4. And now I'm going to take 5 times row 1 and add it to the row 3. So this is going to be 0, this is going to be -1, this will be -10 plus 9 is -1. Okay, one more step. I don't need to get it in reduced row echelon form. If I can get it into just row echelon form and tell that there's 3 pivots. Having 3 pivots tells me that the matrix also, if n's equal 3, tells me that the matrix is invertible. So let's just look at the pivots. That's actually easier than going all the way to the identity matrix. So I'm just going to leave rows 1 and 2 alone and just focused on pivots here. And now to eliminate the -1 in row 3, column 2, I'm going to take just row 1 added to row 2. So we'll have 0, 0, 3. Okay, so I have 3 pivots. For a 3 by 3 matrix. And over here it says if A has n pivots, then A will be invertible. Okay, and that's what we were trying to find. Is A invertible? 3 pivots for a 3 by 3 matrix means that A is invertible. So look at the conditions and see what's the easiest thing to show based on the fact that we're given this matrix. So looking at the number of pivots is easier than checking the columns to be linearly independent. We would have to solve a system there, or even reducing it all the way to an identity. Just get the number of pivots. Okay, matrix multiplication we saw previously is composing linear transformations as well. So if we had A times B of X, or A times B times X, that was equivalent to A times B of X. Okay, so what we were doing here is we were composing the 2 functions. We applied B to X first, and then we applied A following that. And that was equivalent to just the product of the 2 matrices. So now if a matrix is invertible, that means that A inverse times AX would just simply be X. Okay, so geometrically what that's saying is that if we start with an X over here, this is the domain, and over here would be the codomain. Okay, if we start with X, multiplying by X here takes us to an element in the codomain, or the image of X would be AX. But now, the inverse just goes backwards. The inverse always goes from the codomain back to the domain. So it would be coming back this way. So multiplying by the A inverse is just equivalent to applying the inverse now to the matrix AX, to the vector AX. And we know that's equivalent to A inverse times A times X, and we know A inverse times A is simply the identity. And the identity times any vector will just be the vector itself. Okay, so that's how we can handle compositions of linear functions. We're composing the product by B, and then we're multiplying by A, which is applying the linear transformation associated with that standard matrix. Okay, so now a linear transformation, we're going to tie these back to those standard matrices again. A linear transformation T is said to be invertible if there's a function S so that S of T of X and T of S of X is equal to X. Now we know that if we have a T, if it's a linear transformation, we know that there's some standard matrix so that T of X is equal to AX. So we'd say X is taken to the vector AX under that transformation. Okay, so all this is saying that is if T is invertible, then there will be some matrix S that comes back. So that's like that inverse function that it corresponds to the inverse matrix. So we know that if T is invertible, well, this theorem states that if T is a linear transformation and A is the standard matrix for T. Okay, so just that's the situation that we've got from here. T will be invertible if and only if A is an invertible matrix. Now, if and only if means that if T is invertible, then A is an invertible matrix. And if A is an invertible matrix, then T has to be an invertible transformation. Okay, so if and only if means you have a conditional going both ways. If T is invertible, a transformation, then we'll automatically have that A is an invertible matrix. And the if and only if means it goes backwards as well. If A is an invertible matrix, then T is an invertible transformation. Okay, so if we know that there's a function S that is reversing the transformation of T, so it's taking, we started with an X here, T of X was in the codomain. If S goes right back to the X, or even if we started with something over in the codomain, transformed with T and came up with X. If both of those work, then what that means is that the S is just the inverse of the function T. So you did inverse functions back in college algebra, so this should look somewhat familiar to you. That's what the property of an inverse function is, and that's exactly what a transformation is. So this is just tying it to the matrices that perform that transformation. So if we know that S and T are inverse functions or transformations, then we know that S can be defined by the inverse matrix multiplication. So X is T accomplishes is accomplished by that matrix multiplication A, and so S then will be accomplished by the standard matrix A inverse times the X. And so that will be a unique function that makes both of these two statements true. Okay, so now let's consider one problem here. What if you were told that you had a one-to-one transformation T from Rn to Rn? Now that doesn't mean it's necessarily on 2. It's just one-to-one. But the two spaces are the same. The codomain and the domain are the same. Well, back in section 1.9, we had theorem 12 that said that if T is a one-to-one, then the columns of A were linearly independent. So that's tying the transformation to that standard matrix. Now, we have the invertible matrix theorem now that says that if the columns of A form a linearly independent set, that all of these other things are equivalent to it, which means then that the matrix A is an invertible matrix. Or that means that the linear transformation A to AX maps Rn onto Rn. So we now know that the matrix A is invertible And we also know that the transformation will be on 2. Okay, so we have then that by the invertible matrix theorem, and sometimes you'll see that just written as IMT, we have that A is invertible, since we knew that the columns of A were linearly independent. And we know that the transformation and T, which is the transformation from X to AX, is 1 to 1. Okay, and so that is, I'm not 1 to 1, on 2. And that was option I in the invertible matrix theorem. Okay, so get familiar with these conditions and be able to use them as you need to. So I definitely would print that out.